All right. Can you see the screen as well? It's visible.
Yes.
Right. Okay. So, right. So last time we did a problem that involved capacitors, and we figured out the equivalent capacitance and the charges and the potential difference across the plates of the capacitor. So the problem was dealt with multiple concepts as well in the in working with capacitors. Then we started with what capacitor really is, right? So we have been so far saying that it stores charges, but the thing is that it really does not store charges, but instead it basically stores energy, right? And we saw that why does it not stores charges? Because if I take this example where you have these plates of capacitors positively and negatively charged, uh, the both of them are equal and oppositely charged, and hence the net charge on this capacitor would be zero, right? And which would mean that basically then no charge is stored, right, on a capacitor. But then how do we use a capacitor? Why do we say that it stores anything for that matter? And that comes from the fact that there is some work being done in separating those charges across the plates, right? So keeping these charges separated like this, work is being done, and because of the conservation of energy, that work or energy cannot just be lost into nothingness, and in fact it's really stored between the plates of the capacitor, and that is how you define the energy that a capacitor stores in its plates, right? And this energy stored can be mathematically written down by considering this equation, Q is equal to CV, and having a graph plotted between the potential difference across the plates and the capacitor, right? And if I look at this graph, basically, if I were to find out the area under this line, I can write down the expression for energy stored, right? Because energy is basically the product of the charge times the voltage with the potential difference across the plates, right? And so if I use this thing in this example, in this expression, and I look at this graph, then I can immediately see that the work that is being done to separate those charges would be the area under this triangle. And we know that that work can be written as half times Q times V. This should be, this was Q, right? By mistake, I wrote C. It's the charge stored. So this is the work done, and with work that is being done to separate the two charges on those plates, right? Positive and negative charges. Now, the question is, how can you physically understand what is this half, right? Why do we so mathematically it's clear that it's the area under the curve or the straight line, which is just a triangle, which is the energy stored in a capacitor. But physically, why should there be a half, right? So we saw, so energy is just Q times V, right? So why is it not just QV? Why is it half of that value? And the answer really lies in the fact that if I go back to the picture of this capacitor, actually I drew a very big capacitor. So this is the battery, positive and negative terminals of a battery. Now, when the battery is attached, these plates are charged, right? Positive and negative charge. So first of all, the charge is going to flow onto the capacitor plates, right? There is no potential difference that is opposing that particular flow. So the charge is going to, because of the battery attached, the charge is going to flow onto the capacitor's plate. And so if the more charge flows, the potential difference starts to increase, right? The potential difference. So because again, Q is equal to C times V, the capacitor is not changing, right? Because we are using the same capacitor. So the more charges that the plate accumulates, the potential difference starts to increase between the plates. And if that potential difference starts to increase between the plates, then clearly more work will be done, right, in keeping the plates separated, right? Because potential difference is really like a push to the plates. So I have to do more work to keep the plates now separated. And it can be seen from this equation, work done, which is half times QV. So I increase the potential, work done has to increase. Now, the average potential difference is equal to half of the maximum potential difference, right? So you can say that this 1/2 is just attached to this V, right? So basically, its work done is Q times half of the potential difference. And that is again coming from the fact that it is basically reflecting the average voltage as the potential difference changes when the capacitor is being charged, right? Because there are two plates, right? There are two plates across which you have this potential difference. And so to average that out, we only use V by 2, right? So does that make sense? This 1/2, does this make sense? Do you understand why do we have this half in my equation for the energy stored inside a capacitor? Could you repeat the last part? All right. Okay. So don't wait for me to ask if you understood it. If you did not get it, just stop me and let me know that yes, I'm not understanding this. Could you go over through this again, right? Okay, so we basically wrote down the expression for the work done, right? Work done, which is a half times Q times V. And because energy is defined as the product of the charge times the voltage, we can also check that by using the dimensional analysis, right? Where you can just check the units and the units match with the units of energy. So we can just write it as a half times Q times V, right? Now, this half mathematically came from this thing that it is the area under this line, under this V versus Q charge graph, right? But physically, why do we have this half? Why did this make, why did the graph make this line with where we were just finding out the area under a triangle, right? Mathematically, you can just say, okay, we found the area under the triangle, so that's why there is this half, because it's just half of the triangle. And mathematically that makes sense, but physically, why is the question was, why is there this half? And it comes from the fact that when I attach the battery to this capacitor, right now, the charge is going to start flowing from the battery to the plates of the capacitor, right? And the more charge that it flows onto these plates, the more potential difference there will be across these two plates, right? Because Q is equal to CV. That's the mathematical expression for the charge relating with the potential difference across the plates. Now, if the potential difference is increasing, so more work has to be done, right? So the more charge flows, the higher work that I have to do to keep the plates separated apart. Now, a capacitor consists of two plates, right? So I want the average voltage across the plates of the capacitors in my equation. And the average voltage would be V by 2, right? Because there are two plates. We are concerned with two voltages, right? One voltage is across this plate, positive, and one voltage is across this plate. But remember, after this charging happens, the plates, there is net charge is 0. So there are equal amounts of charges on both the plates, right? So that means if there is V over here and there's V over there, then the total voltage will be something like 2 times of something, right? And we just need the average value of that. So we divide that total voltage by 2 to get the average voltage as the potential difference is as the potential difference is changing due to the charging of the capacitor. So is it any clear? If anyone still did not quite get it, you can let me know. Ask me if there is still any confusion. Okay, all right. So that's this right now. You don't see capacitance in this equation yet, so we can include for that capacitance as well in my equation, because we know that this thing Q is equal to C times V. So work done was half times Q times V. So I can just substitute this Q in this expression to get half CV squared, right? So sometimes it's just useful to express the energy of the capacitance in terms of the capacitance itself, right? And the potential difference, obviously. So this is how you can figure out the total energy stored inside a capacitor, right? So for example, now you can pick any capacitor and see what capacitance does it have, and then you can just figure out the energy that that capacitor will store by using this expression for energy stored inside a capacitor. Right, so now we can extend this thing by by understanding the concept of how this thing was happening, how the charge was changing, and that change in charge, as in it was storing charge, right? So the more charge it stored, the more potential difference was changing. So if the potential difference is changing, then essentially this equation should look like half C change in potential difference squared, right? Which means that you can write it as half C VF squared minus VI squared, right? where Vf is the final potential difference and Vi is the initial potential difference at any point in time, right? So you can understand this better by considering an example. So suppose that if I have a capacitor and this capacitor is of 400 microfarads, right? And it is attached to some battery, right? It is attached to some battery and then it's removed, and in such a way that the capacitor starts to discharge. When this capacitor is going to discharge, what would happen to the potential difference across the plates? What do you expect? What should happen to the potential difference across these plates? As in, should it increase? Will the potential difference across the plates stay the same, or will it decrease if the capacitor is being discharged? Any ideas? Okay, you said Alish, you said increase. Sorry, no, yeah, it will decrease, right? Can you? Okay, so it will decrease, right? Because the capacitor is discharging. When it's discharging, it's losing charge, and if it's losing charge, then the potential difference across the plates will also fall, right? And because of Q is equal to CV, and if the potential difference falls, then that means that the energy that it can store will also fall, right? So so the problem statement is something like the capacitor is discharging, and it discharges from a value of 12 volts to a value of 9 volts, right? So sorry, so it's discharging, so this should be 9 and this should be 12, right? So final is lower, 9, and the initial value is 12 volts. So if I compute, so now I can, it's very simple. I can, if I want to work out the energy, you can say that it would be half C Vf squared minus Vi squared. That's pretty simple. But what about the physics? As in, what is this energy? Physically, what is this energy? Is it the energy that is stored inside the capacitor? Any ideas? It is the change, right? So it is the change, or you can say because the capacitor is losing its charge, so it has to be losing its energy, right? So this is the energy that is lost during the discharge process, right? So it is the energy loss. And then you can simply compute by putting in the values in this expression, which would be half times 400 into 10 raised to power minus 6 for micro, and then farads multiplied by Vf squared, which is 12 squared minus 9 squared, right? And this would be volts squared. And this gives you the energy that is lost, or the energy changed during this discharge process, as 0.0126, right? And you can, well, just so this would be in joules. So there should be a negative sign over here, and that comes from the fact that this is 9 and this would be 12, right? Because the final voltage is lower than the initial voltage. So this would give a negative sign. And then this negative signature is also showing you that the energy is lost, right, by the capacitor during this process of discharge. And it should make sense, right? Because if you're at the capacitor, you're discharging a capacitor, you're taking its charge away from it, then it would be, then energy should be lost, right? Because now the plates of the capacitors, it would be easier to keep them apart, right? Because the potential difference has dropped as well, right? And the potential difference between the plates was what was keeping the plates closer and closer and closer together. So if I increase the potential difference, the plates start getting closer together. But if the potential difference falls, then the plates move further apart, and which means that the energy is being lost in this process, right? So does that make sense? Is this clear? All right. So a very basic and exactly almost the same similar type of a problem is that if I have another capacitor, right, and let's connect this one to a battery as well, and suppose that it has 470 microfarads, and it's connected to a battery, and suppose the battery is 12 volts. Now it's connected to this battery, and I'm using this battery to charge this capacitor, right? I want to figure out what energy will this battery store inside the capacitor, right? So I want to figure out the energy stored in the capacitor while I'm charging this capacitor, right? So if I use the battery of 12 volts, what energy is it capable to store? So it's very straightforward, right? What expression can I use to compute this energy? If you remember, this energy stored is just the work done in keeping these two plates apart, and the work done is basically Q times V, right? Yeah, so you got the equation right? So half CV squared, and you have this negative signature to half the voltage, and so you can just substitute for Q is equal to CV and just write it as half CV squared. Okay, so if you're doing an exam or a test, then you can directly write this equation as well. W is equal to half CV squared, right? So you don't have to derive it from this relation, but sometimes you don't tend to remember some expression, so it's easier to remember just the basic expression, and then you can derive the rest from that basic expression, right? And now it's pretty straightforward because you just put in the values, half 470 into 10 raised to power minus 6 farads times the square of 12, right? So 12 squared, volt squared. And whatever this gives you would be the energy that this would be stored inside the capacitor because of the 12-volt battery supply. So what this means obviously is that if I use a different type of a battery, then I'll be storing a different different value of energy in the capacitor. So the energy that is stored inside the capacitor depends upon the battery that I'm using, right? And it obviously also depends on the capacitor. So the higher the capacitance of a capacitor means the more energy that it can store. And this was something that we were previously talking in terms of charge, right? So the more charge it would be storing, but really it is the energy, right? So this is 3.4 into 10 raised to power minus 2 joules, right? So you can see it's a very a minute amount of energy being stored inside the capacitor, right? So so does this make sense now? Why do we say that capacitor does not store charges, but instead it stores energy? Is that clear for everyone? Right. So let's do another problem, right? And so after this problem, we'll end with capacitance, and we'll start magnetism, right? Magnetic fields and those interesting things. All right, so again, I'm going to use a capacitor, and let's charge this capacitor. So suppose that I have a capacitor connected to a battery supply, and let's say this is a 12-volt supply, and you have a 50 microfarads capacitor. Now, I'm using this system to charge this capacitor, and immediately what I do is I remove the battery and I attach the battery across another 50 microfarads capacitor, right? So what I'm doing is, the situation is again something like I have a capacitor of 50 microfarads, and it's charged using a 12 voltage of battery supply, and then it is disconnected from the battery and then connected across a second 50 microfarads. So this was the initial situation. Now the situation may look like this, right? Or it could have been connected in parallel, right? So initially this was happening, and after that we just removed the battery and attached another capacitor, right? Now, so this is the situation at hand. Now, first, let's compute the charge on the first capacitor, which was this one, 50 microfarads, before it is connected to the second capacitor. So let's see what charge did it store before I removed the battery, right? So charge stored before removing the battery. So that's pretty straightforward, right? Because you have a battery supply that's supplying the voltage. You have the capacitance. So you just use Q is equal to C times V, which is just 15 to 10 raised to power minus 6 farads times 12 volts, right? And this gives you a charge of about 6 coulombs, 6 into 10 raised to power minus 4 coulombs, right? So this is the charge that the capacitor, 50 microfarads capacitor, has stored in it. And then the battery is removed, right? So this 50 microfarads capacitor has been charged with 6 into 10 raised to power minus 4 coulombs, right? And now I bring in another 50 microfarads capacitor, and I attach it to this initially charged capacitor, right? Now, let's also work out the energy that would be stored in the first capacitor, right, before I remove the battery. And that's very simple. Again, you can just use this expression W is equal to half either Q times V, because now you have the charge, or you can use half CV squared, right? Because capacitance is also provided. So you just put in the values, and this gives you around about 3.6 into 10 raised to, let's just write it millijoules, right? Okay, so that was the easy stuff. Now let's try to figure out the charge on each capacitor when they're connected together, right? What would be the charge on each of these capacitors when they're connected together? Any ideas? Any suggestion? It would be half, right? Exactly. So when these when the capacitor, the charged capacitor is connected with the other one, after removing it from the battery, the charge will be shared between these two capacitors equally, right? And this again comes from the conservation of charge, which was also one of Kirchhoff's law. And so if the charge on each capacitor will be shared equally. Due to the conservation of charge, right? Due to the conservation. So that means that the charge on first capacitor would now be 3.0 into 10 raised to power minus 4 coulombs, and the charge on the second capacitor will also be 3.0 into 10 raised to power minus 4 coulombs, right? So we just halved this value. Right. Okay, so next, let's try to, which would be the part 4, figure out the potential difference across each capacitors. What do you think? What should be the potential difference across each capacitor? As in the plates of both of these capacitors, right? Between the plates of both of these capacitors. Any ideas? I'll give you a hint. This, you can look at this equation. Q is equal to C times V. Right now, capacitance for both the capacitors is 0. Right. Sorry, I said 0. I meant same. Yes, Alicia, you're right. It should also be half, because capacitance is same. So if the charge becomes half, then voltage becomes half. Right. So cross of the capacitors should be half of the original value of the capacitance, which means that V1 would be 12/2, which would be the same for V2, right? And this is just 6 volts. All right. Now, finally, let's figure out the total energy that can be stored. So this would be part 5, when the two capacitors are connected together, right? What would be the total energy that this system would be able to store? Suppose that the capacitors are connected together. Like, what do you think? What should be the total energy? So can I do this thing? If I find out the energy on one of the capacitor and then just multiply it by 2 for the other capacitor, would that make sense? It should make sense, right? Exactly, right. So because energy is just a scalar quantity, and you can just add so energy from one capacitor and the energy from the other capacitor, and the superposition of these energies, as in the sum of these energies, would be the total energy of the entire system of 2, or well, in this case, 2 capacitors, right? So I can easily compute the energy on energy. How do I say this thing? Energy stored when 2 capacitors are connected, right? All right, so now I know that I can use this expression for energy, half times Q times V, right? And so this would be half times, what would be Q? I'll just sir, before starting a new topic, can we do some past paper questions? Yeah, sounds good. Sounds good. Okay, so from electricity, right? All right, so I'll prepare some of the questions from this topic, and we'll do those tomorrow. Right. So this would be 3.0 into 10 raised to power minus 4 coulombs times whatever the voltage is. It is 6 volts, right, for each capacitor. Because remember, this is what we saw, that each capacitor stores half of the total voltage, which was 12 divided by 2, and that's 6. So this would give you an answer. And if I want it for both of the capacitors, then I'll just multiply this by 2, right? Or just add them 2 times. So this 2 would cancel with this one. And this gives you the result 1.8 into 10 raised to power minus 3 joules. Right? So that's the total energy stored in the composite system of 2 capacitors connected together. So is that clear? All right, Hasib, yeah. So I'll prepare some questions from this